Today we study divergence and Stokes theorem. We first study the elementary vector calculus. Derivative of two functions, derivative of the product of two functions, f1 x times f2x can be computed by taking the derivative of the first vector and multiply the original one, and take the derivative of second vector and multiply the original one for the first vector. If we factor out the original product, then this one is f2, so f1 is missing, so f1, 1 over f1 is there. The next one is 1 over f2 is there. If we extend this relation to the product of n functions, so product of f1, f2 to fn, then the derivative of this product of n functions can be computed as a product of n functions summation over k that runs from 1 to n, the 1 over k, and derivative of that vector. This is the product derivative, first order derivative of the product of the two functions, but we can compute the nth order derivative of a product of two functions. For example, fg prime equals f prime g, fg prime, fg double prime equals, take the derivative one more time, so f double prime g, f prime g prime. This one, f prime g prime, f g double prime. So f double prime g plus 2 times f prime g prime plus f g double prime. This overall factor is a combination. Among n derivative, there is a way to distribute k derivatives and n minus k derivatives. So that is combination n factorial over k factorial and minus k factorial. This combination factor is multiplied, and sum over k runs from 0 to n. Next, we deal with some cross products. The orbital angular momentum L for a particle of momentum p, orbital angular momentum is x cross p, and p equals the mass times the velocity. The ith component of the orbital angular momentum of the particle A cross B. The first component is A2 B3 minus A3 B2, and so on. That can be expressed as a determinant E1, E2, E3, A1, A2, A3, B1, B2, B3. That determinant is epsilon I j k xj pk. Here repeated indices J and K are summed over. So here J runs from 1 to 3, K runs from 1 to 3, and I is 1, 2, or 3. Let E1 hat is I hat, and E2 hat is J hat, and E3 hat is K hat, the unit vector of the Cartesian coordinates. Then the angular momentum L is, because L vector is E1 hat L1, E2 hat L2, E3 hat L3. Therefore, sum over I from 1 to 3, EI hat Li. And Li has been computed in here. So, sum over I runs from 1 to 3, J from 1 to 3, K from 1 to 3, EI hat epsilon ijk xj pk. This is the answer. The first order time derivative of the angular momentum is the torque. Here, this is d over dt, something like. So, time derivative of x cross p. The derivative of x first and cross p. Derivative of p and cross x. Now we remember dx over dt equals v, and p equals m times v. So v cross v equals 0 vector. So this one does not contribute. And this is a force. So position vector cross force, that is a torque. The time derivative of work is power. The force, displacement, infinitesimal displacement, and the x, that is F times velocity. This is power. Exponential function. Euler number, that is this kind of number, is defined by the limit as n goes to infinity, 1 plus 1 over n, with the power of n. And actually, this one is same as 1 over n squared alpha q beta. Indeed, if you expand, you find that in the limit n goes to infinity, these two contributions vanishes completely. This one is the example. So if we substitute alpha 1, alpha 2, alpha 3 with n, n squared, and q, higher order pieces will disappear absolutely, and the answer is e to the alpha 1. If fx is differentiable to all orders, we can make a Taylor series expansion. And actually, f of x plus a with the Taylor series expansion is sum over k runs from 0 to infinity a k factorial f of x. So we have combined this and made it as an operator acting on f of x. Then we find that it is this exponential of this operator. So this is nothing but a Taylor series expansion of a differentiable function. We can extend this idea to n variable function. X is a Euclidean vector in n-dimensional Euclidean space. F of x plus a can be expressed as a dot gradient of f of x. We have a missing vector 1 over k factorial in here, 1 over k factorial in here. The scalar product of two Euclidean vectors is a1, b1, a2, b2, an, bn. Therefore, a dot gradient, the gradient in the Euclidean, n-dimensional Euclidean space is x1, x2, xn. So, therefore, if we make use of this definition, it's consistent to write a1 partial derivative with respect to x1, a2 partial derivative with respect to x2, and so on, an partial derivative with respect to xn. Matrix exponential function. An exponential of an n by n square matrix. A matrix a squared, a cubed, this one can be defined only if the number of rows and number of columns are the same. That's the reason why we introduce n by n square matrix. If the matrix sum converges, then we define that matrix to be exponential a. This is an example of exponential of a square matrix. We have studied the rotation matrix in 2 dimensions. X, Y. The unit vector is 1, 0. This is 1, 0. After rotation, this coordinate is cosine and sine. So 1, 0 transforms into cosine theta, sine theta. And unit vector 0, 1 on the rotation about the z-axis by an angle of theta, this is minus sine theta, cosine theta. Therefore, 0, 1 transforms into minus sine theta, cosine theta. A matrix that transforms these two vectors is this and this. Therefore, we call this one to be R theta, that is a rotation matrix about the z-axis by an angle of theta. If we multiply two rotation matrix, what we obtain is, for example, CS minus SC, same angle, in the case of same angle, CS minus SC, cosine squared minus sine squared, 2 cosine psi minus 2 cosine psi, cosine squared minus sine squared. If the angle is the same, then it is cosine 2 theta, and minus sine 2 theta, sine 2 theta. In a similar manner, if we multiply two different angles, in either way, it is commutative, and the result is like that. We have made use of cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2, or cosine alpha plus beta, theta 1 plus theta 2, and sine theta 1, cosine theta 2, sine theta 2, cosine theta 1 equals sine theta 1 plus theta 2. So using this way, this one must be raised. So if you apply this idea, R theta can be understood as multiplied by n. So that means rotate 1/n of theta by n times, we have R theta. And this is true even in the limit n goes to infinity. We already know the Taylor series expansion of sine and cosine are given in this way. We can express this one. R theta over n is cosine theta over n, cosine theta over n, minus sine theta over n, and sine theta over n. As n goes to infinity, theta over n goes to 0, very small. So we can make an expansion of cosine and sine. Substitute x equals the theta over n in here. Then this one becomes this. Okay. This is sine. This is proportional to x, neglecting the third power, theta over n. This one is 1 minus x squared, 1/2 x squared. plus something. So this is 1 plus 1 minus theta 1 squared. So we remember that any higher order piece in the expansion, and here there's 1 over n squared something, or 1 over cube something. They are all vanishing. We need to have a power n. This one vanishes and only this one contributes. And this is actually the exponential. Now this is the coming from this, and this expansion is included in here, and that can be consistently neglected because of our previous discussion. Where is it? Where is it? Here. Next we consider scalar, vector, pseudoscalar, and axial vector. An object invariant under the transformation. Vector replace vector with minus vector, but invariant. Then we say it is a parity even. An object changing the sign, keeping the magnitude the same under this transformation. Changing the sign is a parity odd. Parity even, x such as a vector replaced with a minus, result is the same, parity even. Result is opposite, parity odd. Displacement, velocity, momentum, force, they are all parity odd. And three components they have. We call they are vectors. In addition, gradient operator, we remember potential energy minus the gradient of potential energy minus gradient of potential energy is the conservative force. So force is a vector. This gradient is a vector. It's a parity odd. Scalar product x dot y, where x and y are displacement vectors, is parity even. The angular momentum are cross p, x cross p, and torque. These are two vectors, but if we substitute x with minus x, f with minus f, the final result will be the same. So this is a parity even. Parity even and has three components. So it is a vector, but it is not a real vector. It is a vector with opposite parity, the parity even, that is called axial vector. Axial vector. There's also pseudoscalar. Scalar, for example, x squared, radius squared, it is a positive, right? But x cross y dot Z. This is a triple scalar product. We call this is a pseudo-scalar, because if we replace these vectors with negative sign, we flip the sign. A scalar, we substitute minus x, scalar product, it is still x squared, is invariant. So pseudo-scalar, such as a triple scalar product of vectors, has the parity odd. Scalar has a parity even. The difference between just a simple vector or vector field is a function of position all over the space. Scalar field is the same when you substitute vector with a minus vector invariant. Pseudo-scalar, if we substitute a vector with a minus vector, we end up with the result is over negative sign, is a pseudo-scalar. So absolute value of x is a scalar. If phi is a scalar, gradient is a vector. This is a vector and this is a vector. Cross product of two vectors, axial vector. Electric field, we only studied the electrostatic potential's gradient is a electric field. So electric field is a vector because charge times electric field is a force, and force is a vector. And this is a vector. Gradient operator is also vector. Phi is a scalar. Because E is a vector, F is a vector, E is a vector, so later we will learn that this is a vector potential, magnetic vector potential. And this is a vector. In a similar manner, magnetic field B is core A, and this is a vector, this is a vector. Cross product of two vectors, this is an axial vector. So B, magnetic field, is an axial vector. A is a vector. Gradient, divergence, and curve. Vector V is there, and position vector can be expressed in either way. Here, x1 stands for x, x2 stands for y, and x3 stands for z. So, vector has three components. v1 stands for vx, v2 stands for vy, v3 stands for the z component. The gradient operator is x-axis, the x component is the derivative of x, y component is derivative of y, and z component is the derivative of z. So using 1, 2, 3 notation index instead of xyz index, it can be written in the form I runs from 1 to 3 ei hat xi. In the electrostatic case, electric field is electrostatic potentials minus gradient. So this potential x, y, z derivative and put negative sign and multiply the unit vectors along the x, y, z axis. Hence, this should be this one, and this one should be the x component of the electric field, y component of the electric field, and z component of the electric field. The divergence of a vector field is defined by divergence is x components x derivative, y components y derivative, z components z derivative, and their sum. If we use index 1, 2, 3, it becomes easier, and it can be expressed in terms of the summation over I, 3i's derivative with respect to xi, and sum over I. This is divergence. And curl is written in this form, and x component is expressed as this, y component, z component. In the determinant form, I, j, k, unit vectors, differential operators, and vector. If we use 1, 2, 3 notation, E1, E2, E3, hat, round x1, round x2, round x3, and V1, V2, and V3, determinant. We can express this one in terms of the linear combination of, there's a plus sign, EI, and I component is epsilon Lebesgue tensor, epsilon ijk, and derivative with respect to xj, and vector of k component, and sum over I, j, and k. Vector differentiation. We have a position vector, x component is x1, y component is x2, and z component is x3. Radius r is the magnitude of vector x, that is the square root of x1 squared, x2 squared, x3 squared. We find the partial derivative of, for example, x1, x1. This is 1. Partial derivative of x1 with respect to x2, because they are different, is 0. x1 with respect to x3 equals 0. In a similar manner, if the two indices are the same, it is 1. If the two indices are different, it is 0. Therefore, round xi, round xj equals delta ij. It is the same, xj, xi. They are this. It is either 1 or 0. I equals j, then it's 1. I is not equal to j, it is 0. Next, x vector, xi. And actually, the numerator is a sum over j from 1 to 3, ej hat xj. This is constant. Therefore, it is j from 1 to 3, ej hat that is delta ij. It is 1 only if I equals j. Therefore, it is I. We have said this. Next, xi. For example, x1. This is we use chain rule. Square root to square root. Then this guy vanishes and this one is 2x1. Therefore 2x1 2 that is x1 over r, where r is this one. Gradient r. This is E1, x1, r, and so on. Round r, round x1 equals r x1. Therefore, E1, x1, E2, x2, E3, x3. Actually, this is r, E1, x1, E2, x2, E3, x3. Right. This is x vector. X vector divided by x vector's absolute value. It's a unit vector along the r direction. Next, gradient x absolute value. That is a gradient r. That's a ER. ER hat is x over absolute value of x. Okay. Gradient of f of r. Chain rule. Because it's a single variable function, dfr over dr and gradient r. And gradient r is here. So this is er hat okay. Partial derivatives are commutative. if the derivative exists, they are the same. In a similar manner, for any components xi, xj, xj, xi. Levi-Civita tensor is anti-symmetric, and Kronecker delta is symmetric. So epsilon ijk, delta jk, this is anti-symmetric, and this is a symmetric. Any anti-symmetric matrix multiplied with symmetry matrix is vanishing. Kerr gradient. So ith component is epsilon ijk, jk anti-symmetric, jk partial derivatives are commutative, symmetric, anti-symmetric, symmetric product is 0. Total differential. A function and it's a shift by varying the argument from x to x plus delta x. Then we say delta f. And this shift can be computed by making use of Taylor series expansion. And Taylor series expansion, we have seen Taylor series expansion is exponential delta x derivative of fx. This exponential function operator can be expressed as a limit n goes to infinity 1 plus 1 over n delta x derivative with nth power. And after expanding the expression, we have the expression that is proportional to delta x. And the leading term has delta x, and next to leading term has delta x squared, and so on. And as delta goes to 0, delta x goes to 0, we take the ratio of delta f of x with respect to delta x, and take the limit n delta x goes to 0, the remaining pieces is absolutely 0. So derivative is expressed as the limit of delta f over delta x as delta x goes to 0. If a function is a function of multivariables, for example, n-dimensional Euclidean vector, so n coordinates, then we extend this idea to the n-dimensional case, and the variation of the function due to the variation of the coordinate in n dimension is of the form, sure, there is a 1 over k factorial is missing, and 1 over k factorial is missing. As the magnitude of delta x vector goes to 0, this one is the leading contribution is the first term, and after that delta x squared or higher order, absolute value of delta x squared or higher order. So As delta x vector goes to 0, the differential, we call this a total differential. The limit of the limit of the change in the function due to the variation of n variable. We compute the total differentials of various functions. For example, R's total variation, total differential. R depends on x, y, z in three-dimensional space, and gradient of R and differential, total differential, their scalar product. We already know round R over round X is X over R, and this one Y over R and Z over R. What happens to the case of total differential of R to the nth power? This is again gradient R to the n. Chain rule can be used, and this is n times R n minus 1, and gradient R is already obtained. We copy this result in here. As a result, these are z over r, y over r, and x over r. We factor this 1 over r to have n minus 2, x dx, y dy, and z dt. What happens if I substitute n equals minus 1? Then is total differential is 1 over r. That is closely related to potential, electrostatic potential. The result is we can substitute n equals minus 1, or we can compute separately, independently. The total differential for a time-dependent scalar field is given by, until now we only consider the spatial coordinate. The time dependence also appears, then we have to add this contribution too. Electric field from electrostatic potential. This is the electrostatic potential due to a point charge Q at the origin. And we make use of the previous results that we have already obtained to find the electrostatic field. So electric field minus gradient phi by making use of this potential V. Phi equals V. The gradient of x, we already obtained the unit vectors. This one was R. R's xi partial derivative is xi over R, and function of R, so derivatives are like that. Finally, we obtained the electric field by computing minus gradient potential, and gradient 1 of R, gradient 1 of R, we already obtained. As a result, we reproduce the electric field that corresponds to the Coulomb's law of force due to a point charge at the origin. The divergence of electric field. We first computed the gradient to find the electrostatic field from the electrostatic potential. Divergence of the electric field can be computed in such a way. Electric field is minus the gradient of potential, and we obtain this. And the unit radial vector can be expressed as x vector divided by magnitude. And this is this. And you follow the detailed calculation shown below, and you find that, for example, this one. This is the x component. First, we can take the derivative of this. And second, we can take the derivative of this. And this is 1. It's 1 over r cubed. And this is minus 3 x squared over r to the 5th. Just remember this calculation. And this is true for x component. For y component, the first term is the same, and second term is x squared is replaced with y squared. And third one, still 1 over cube is the same, minus 3 z squared. If we add the first 3 terms, we have a 3 over r cubed, and the second one, x squared plus y squared plus z squared r to the 5th power. This one is r squared. Therefore, we have 3 r cubed, 3 over r cubed equals 0. Note that this differentiation is possible only for r is not 0. Because at r equals 0, the function is not differential. So, divergence E, what we have done is divergence E's calculation. The electric field divergence is vanishing in free space. The electric field divergence is vanishing in free space means because charge is at the origin, except for the origin where the charge is placed, electric field's divergence is always vanishing. That is very, very important. And electric field's divergence at the origin, where the point charge is placed, it seems to be non-zero. But we are not able to compute the exact value at the moment. Let us consider the divergence theorem. Divergence theorem is such that this is divergence, and we carry out the volume integral in arbitrary volume containing the origin. We have seen that the electric field is vanishing. This is a specific to E field only. For simplicity, divergence E equals 0 in free space. If there is no charge, divergence E was 0. So this is the integrand. Integrand is 0 except for the origin. Divergence is a volume integral over space is 0 except for a single very tiny volume called V0. It is V. And because divergence E equals 0 everywhere except for the point where the charge is placed. So we carry out the volume integral. This volume integral vanishes everywhere except for a very tiny volume V0 that contains the origin. This greatly simplified the calculation. Now, there is the origin, O, where the charge is placed. So we have delta, 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 centered at the origin. So x ranges from minus 1/2 delta to half delta. Y, z has the same range. And we have a Q whose volume integral does not vanish. And divergence can be computed in this way. XYZ integral over the given range. And integrand is x components x derivative, y components y derivative, and z component. The first term, for example, this one is a derivative of x, and derivative of x integrated over x. So we can integrate x integral. Remaining integral is a 2D surface integral of the xy plane, yz plane. The second term, this is a y derivative, so y integral can be carried out, and z integral, and so on. After x integral, what we obtain is the final value is x value is upper bound, this upper bound, subtracted by lower bound of x coordinate. The second term, upper bound of the y coordinate, lower bound of y coordinate, and z component, upper bound of z coordinate, lower bound of z coordinate. So, first term, z, x, y. Here, x equals this surface. And the other surface, this one represents x equals minus 1/2 of delta. We find this direction, the surface facing outside. At this point, the surface facing backward. Therefore, sum of these, including the negative sign, is actually E dot dA on the x equals 1/2 of delta plus x equals minus 1/2 delta E dot dA. In a similar manner, actually this negative sign represents the positive g direction, and this is negative, and y, positive and negative. Therefore, sum of these 6 is actually the E field scalar product area over this closed surface enclosing V0. Because divergence E equals 0 everywhere except for the origin, we can modify this closed surface in arbitrary shape as long as this volume contains the origin where the charge is placed. Therefore, we have proved that this one is the same as this, and then this volume integral is extended to the wide area. The surface integral can be extended to everywhere as long as this volume V includes the point charge Q. As a result, we have proved the divergence theorem. Volume integral of divergence is the surface integral of the electric field, this over a closed surface containing the volume. So this proof is isolated to the electric field that is satisfying the inverse sphere law, but in general, this is true for any vector field. So Gauss law is a straightforward consequence of this divergence theorem. If you substitute the electric field and compute the surface integral, it's trivial to find that Q over epsilon 0, because I have listed all the definite integral to obtain the Gauss law. The differential form of the Gauss law is like that. Divergence theorem is this. We take the volume to be very tiny volume. Then this volume is very small. Subtract divergence E. This one is Q over epsilon 0, and Q is the volume integral of the charge density. So 1 over epsilon 0 here. So subtract these two integrand and take the volume integral. If the volume is very, very small, then the integral vanishes always, but its volume is very small. There is no way but to have this integral to be 0. Therefore, divergence E minus rho over epsilon 0 is 0, and this is called the differential form of the Gauss law for the electric field. If you apply the magnetic field, this is a charge density. As long as magnetic field is concerned, there is no magnetic charge. It is always the magnetic field is generated by the electric dipole only, so magnetic monopole does not exist. So charge density is always 0. So divergence B equals 0 is for the Gauss law, differential form of the Gauss law for the magnetic field. You can prove this by making use of the continuity equation. And because the detailed calculation is given in here, let me just pass. This is the continuity equation that derives from the divergence theorem. Next one is Green's theorem. Because calculus, you learn the Green's theorem in detail in calculus. I do not want to explain very detailed, but it is the answer is completely given in here. So I hope you can follow the whole amount of the Green's theorem, that is for the two-dimensional plane. And this is the component, z component of a curve. Z component, the third component. Then this is a line integral on the plane. That means there's a closed curve that surrounds a surface. The curve of a surface integral is expressed as a line integral along a curve, and that curve is the boundary of the surface. This is the main idea of the Green's theorem in two dimensions. And Stokes' theorem is the generalization to the three-dimensional space. And actually the basic idea is the same. There's a surface S, and there's a boundary, closed curve surrounding the surface S. Here, the circle in this integral means the curve is closed. Close the circle, close the path. Okay. Detailed derivation is given in here. Okay. So today we have learned two important theorems. One is the Divergence theorem and the other is the Stokes theorem. Divergence theorem is especially for the calculation of the electric field, but for any vector, divergence of any vector over the volume is vector's surface integral, and this is a volume and is over the surface, and this surface is closed, and that surface is the boundary of the volume. And because of this, divergence of electric field over the volume was expressed as a scalar product with area vector over the surface, and the surface closed, and the surface is the boundary of that volume. And if we substitute explicit electric field in here, you will find that this charge after integration is charge over epsilon 0 and enclosed by the surface. And this charge is re-expressed as a volume integral, that is 1 over epsilon 0 From this, we obtain the differential form the Gauss Law. And we call this one to be the Maxwell's equation. There are 4 Maxwell's equations, and 2 Maxwell's equations are for the divergence equation that comes from that can be derived from the divergence theorem. Another important theorem is Stokes theorem. Stokes theorem is the generalization of the 2-dimensional version that is called the Green's theorem. And the Stokes theorem is for the Kerr's surface integral. Kerr's surface integral over a surface is always expressed as a path integral over a closed path. That closed path is the boundary of the surface. And this closed path, this kind of integral, that is curl of A's surface integral over the surface. That is called Stokes theorem. By making use of the Stokes theorem, we can derive the differential form of 2D other remaining Maxwell's equation later. In this chapter, in this class, we have seen many useful formulas. I hope you can follow these mathematical formulations. That is quite useful in the future in this class and your future study regarding engineering or mathematics or physics. Okay, that's it for today.